hope that I'm audible. Yeah, my talk is about the discrete time cost trade-off problem, which is actually a very important problem in practice of chip design. I will give a few notes on that later. And that made us for a couple of years now to study also theoretical properties. And recently we got some improvements that are maybe a bit more than just very basic ones. So let me define the problem, and we'll need to define it in a simplified way. So we are given a partial order, which we can represent by some acyclic diagram, and each element or in this set that is partially ordered corresponds to a job that we have to perform. And like when constructing a house, you cannot build the roof before the basement, so you will have some jobs that need to be done before other jobs are done. And that's what this partial order defines. Every job takes some time to be executed. That's some slow time, if you say, put a single worker on that. And that are these red numbers here in this example. And what you can then do, you can go for the longest chain in this order with respect to this execution times and see how long that will take. And in this case, we have here a chain, if you sum that up, that has a total delay of 10. And if you want to be ready within 6 units, then that would be too slow. You have to speed it up somehow. And here we assume that we can put more effort on certain nodes. We can buy for some price, it's the price CV. We can set the execution time essentially to 0, which you might think right now is more than you could hope for, but let's pretend we can set it to 0. For this example, let's assume that the prices are for the time being all just unit prices, they all cost the same. And we could, for instance, by these 3 jobs, speed them up to an execution time of 0. And with that, we see that now the longest chain is actually the one at the bottom here, which has a delay of 6 minutes. Usually, you would have multiple options at a job where you could choose from. But you can always reduce it to this very basic case where you just have 2 possibilities. Either for no price, you get a slow delay, or you pay some price and just speed up your item to delay 0 for paying this price. And that's a basic reduction that was already proposed in the 90s by Spitella. It was probably known even before. You just take a vertex with a choice of different delay alternatives and replace that by a set of parallel vertices, where every vertex represents one of the execution times, and the prices are always the differences to the next faster slower execution time. And once you do this reduction, we have such an input that we call normalized, and that's the basis for further approximation algorithms. Now, the task that we are looking for is, we are given this deadline. We want to find a set of jobs of minimum cost such that when we speed up these jobs, they don't contribute any delay any longer, and the remaining delay of any chain should be at most the deadline. So what is known about this problem? There's one more thing that I want to, that's actually the main purpose of our considerations here, is that here we have the depth of this graph, of this underlying, or the maximum length of a chain in our partial order. We assume that that is not getting too long, so we don't assume a fixed constant, bound on the step, but that is a parameter for us, and we want to analyze the approximability with respect to this parameter. In our application chip design, you can consider these nodes as some small Boolean gates, like AND OR gates that are interconnected by a netlist to do some Boolean computation. And there we can choose some trade-off parameters, materials that determine the speed of them. And so we want to minimize the cycle time of the chip. So we need to speed up certain devices, but speeding up a device costs some power or increases the power. And so we want to minimize the power. And that's an important application. And then in chip design, these paths are typically not getting too long because we have some cycle time, and within one computation cycle, you can only execute a small number of jobs, say. This depth is typically something between 20, maybe 30, not more. While the number of elements can be in the millions. Yes, those are.
So if you pay the price for an element, then the cost of the delay is essentially zero.
Yes.
And you also do pay the price for slowing it down by per unit or so?
Yeah, we have a discrete setting here, so we don't care about a per unit price. We just have these two alternatives. Of course, you could consider the linearization of this, but yeah, I'm not sure, or maybe you rephrase your question. Maybe I'm not getting what.
I think you kind of already answered it.
Yeah.
To some
Yeah,
extent.
That's what that is.
Yeah.
Yeah, that's what that is. So I think there is a reduction to this case.
Okay.
If you have discrete choices.
Sorry.
Yeah, if you have discrete choices. Otherwise, you can also make this reduction and then every vertex would represent some linear function if you run the continuous relaxation. So actually, we looked or used algorithms for the continuous relaxation for many years from the mid-90s, so long before I started looking into this until the mid-2000s. And that was actually the powerhouse of our delay optimization to speed up the signals on a chip. And we applied some algorithm. We did not know about the time, or people that developed that did not know about the time for trade-off problem that much. So they developed an algorithm that is very similar to an algorithm by Phillips and Isuki for the continuous, or for the linear relaxation of this problem, where you speed up along minimum cuts and iterate it. But that's not our topic of today, but we use such models for long already in practice. Yeah, so this depth is typically very small compared to the size of the instance, and that's why it's interesting. Maybe we can get good approximation algorithms in this parameter. Some previous work. So the general problem is strongly NP-hard. Scutella developed some bi-criteria approximation algorithm, trading off of violating the delay constraints and then the cost. And it's also APX hard. And there's a reduction to vertex cover from where you get that there's no 1.36 approximation unless equals NP. And then Svensson showed that if the unique games conjecture holds also, then we cannot hope for constant vector approximation for the general case. With this parameter D, we already applied quite successfully, practice a simple algorithm based on some set cover formulation. Then we can apply the bi-even algorithm and get the D approximation. That is something we want to improve over today. One should know that these results also hold for very small d. That's not so clear so far for Svensson. So in his construction, the depth also increases. Yeah, and we are trying to improve this algorithm, and I will at some point also on our way derive how we get to this D approximation. It's actually quite simple. So the first result will be there will be a D-half approximation. And then we show also that we cannot do better than d plus 2 over 4. Yeah, I'm assuming the unique scale, unique games conjecture, and yeah, so let's first do the first result, so the d-half approximation. And the base for that is an this often is an LP formulation. There are many ways how to model LP formulations, and we use one that is covering LP, and that's why I probably ended up in this session also. So we consider the minimal chain that if we don't speed that up, violates our delay bound. We denote those as critical. And you could consider the set of all such critical chains, and you can also see that those form the clutter. And it's also a clutter, but it's in particular it's the blocker of all minimal feasible solutions. That's if you are familiar with clutter and blockers. But if not, it's also sufficient just to consider B as the set of minimal chains that need to be sped up. So these are chains where you know at least one element needs to be sped up, or essentially precisely one. So that means if we are looking for a feasible solution for each such critical chain, we need to intersect that chain with our solution. And that is this. If these minimal feasible solutions consider them as a clutter, then you have this typical clutter blocker relation. And then what does it mean? That means that F is just a vertex cover in the hypergraph on our round set with these critical chains as hyperedges. Yeah, so we can formulate this integer programming formulation. So we want to choose vertices. We pay for each vertex, and then we want to make sure that for every critical chain, at least one element is put into our set. And there are a couple of problems with this formulation. First is the separation of these constraints is not easy in general, and also for our special case of the time constraint problem, we don't know any, or it's actually NP-hard to separate them, when you can show that by a reduction from partition. But we can at least approximate this LP in polynomial time, where you can round these x values in a certain way with respect to some epsilon that you choose, and then apply dynamic programming similar to NAPSEC. Except that here we proceed along the graph or the underlying chains, but we can approximate this. And that is an important thing, because doing this to achieve the d-half approximation, we need to get a better rounding than just d-half, because we are losing already when solving the LP. Now the good thing is, because our depth is bounded by d, we can trivially partition our elements into levels just by the length of say maximum length of chain of that element. That also means that our hypergraph is departite. So every edge has at most the elements, with at most one element from each set in the partition. Some people define d-bipartite also that it needs to have something from any set. We would call that a d-uniform hypergraph. Here we don't need to have d elements in every hyperedge, but at most d and at most one from every set. Interestingly, so we thought for a long time, we thought about set cover problems. We did not have hypergraphs so much in our mindset for quite a while. And at some point we thought, oh, let's maybe look for hypergraph formulations. And then we discovered actually quite late that Lovas analyzed the gap of this LP, at least for the unweighted case in his PhD fields. I think it was never published elsewhere. You can find it in the PhD thesis, which is written in Hungarian,
I'm so happy to find it.
someone wrote it in his paper. And so we looked it up and tried to understand what he did. So actually, Ziad was a PhD student until May. He took some effort to try to translate these things. And he gave some algorithm which is polynomial but not really efficient. So it creates a huge matrix and then shows that you can pick a certain column from that matrix to do some rounding. And we will give, of course, a similar flavor, but in our eyes, at least similar rounding scheme, which is first only random, and then we will de-randomize it also, and it's actually then an efficient algorithm to round the solution. What one should also keep in mind that the bipartite hypergraph vertex cover problem cannot be approximated better than a factor d². So I said we will also see a no d/4 approximability, but that is because the time-constrained problem is a special case of bipartite hypergraph vertex cover. We don't see how these instances created here relate to time-constrained problems. That's maybe one open question I will also trace in my last slide. So this holds for the more general class of problems. But there is maybe some indicator that this factor is around what we can expect. So, okay. Let's start with a simple algorithm, and that you can also consider as the simple de-approximation to obtain. You can take the solution of our LP, and then for every vertex you round it up to 1, you put it to the set if the value is at least 1/d. Then this is a feasible solution because every hyper edge has at most 3 elements, and we know that the sum of these elements is at least 1, so one of these elements must be rounded up. That's nice. This indicates this rounding scheme. So these are our levels, these are our fractional solutions. And here we have 5 levels, so we have 1/d as our level above which we round up. And what you can already see is that, well, we are sometimes just below some solution. If we would lift this level here a bit, we could get rid of this green solution. We could remove it, make our solution cheaper. And elsewhere, we might, on the other hand, lower it, this level. Yeah, so by having a non-uniform rounding, you can expect a better approximation. And that's what we essentially do. So if you take a threshold for every level, such that they still sum up to 1 as before, for the uniform one, and now you round up a vertex if the value is above the threshold of the level the vertex is in, so L of B is the level the vertex is in, then you can just do the same calculation and see that this is a feasible solution. And it's not clear that it's cheaper, but we will see that when we choose this in a certain randomized way, we can get a cheaper solution. And that is now something that is barely visible here. So we can choose a level for each, a threshold for each level. such that they are distributed in these small intervals that are indicated. You can better see that on here. So we have here small interval, then here. So we actually partition these area from 0 to 2 over d into uniform blocks. And we pick every level from within each block. And we can, of course, not completely do that independently because we need that the sum is 1. But we can do it in such a way that we group the levels into blocks of 2, except for at most 1 block that needs 3 levels. And then we can randomly say we group these last 2 ones. We can select a random level from within its interval, and then that determines also the other neighboring interval. And here we need to do some 3-level distribution. But we can do that such that whenever 2 levels are at least 3 units apart, then these choices are independent. And that's not sufficient. What we also need to do is we cannot always have this.
So this sorry, that sort of for lower levels, the AI
is chosen from a smaller interval, yes.
So I see.
But of course, we cannot always choose the smallest interval on the first level. So we also do random permutation of the levels. And that's what you again can better see on the screen. So we perturb then the random choices that we do assign to the levels. And when you do that, you can now prove that the probability that the variable value is above the threshold of its level, so the sigma is just the random perturbation that we have, then this probability is the minimum of 1 and d over half xd. And this second part then allows us to prove that the overall expected cost of our solution is at most d half over the LP solution. That's good, but that's not quite good enough. We can also, one can do all this deterministically. So for doing this computing the assignment to the levels, we can just solve a matching problem by assigning or computing the expected costs of having a certain interval in a level. And then we can, in these groups of 2 and 3, we can also just compute in n to the 3 time the optimal thresholds inside. So we can easily randomize this. But it's not good enough because it only gives us a d half plus epsilon approximation, because we can only approximate the LP. We don't get this x in polynomial time. So we need to do a little better. And when you look at such an assignment, you see that there is always a gap to the next lower fractional solution in that level. What we want to do is we want to lift the level somewhere to get rid of some fractional solutions that are not rounded anymore, to make our solution cheaper. But we can only do that if we can lower them elsewhere. And that's the idea, to use these slacks to, on most levels, we will lower now our threshold a little bit. And then we can randomly again pick one level where we will lift it by the amount that we have saved on the other levels. We have to be a bit careful. I mean, we have this grouping into blocks of 2 or 3, so we are not lowering the level in this group of this random choice, but only in all other groups. But we can lower the levels in the other groups. So that's maybe better indicated here. So in this red group, we are keeping the levels where they were. For the blue ones, we are now lowering them just slightly above that threshold, where we would pick another element into our set which we want to avoid. And when you do that, you can save a little bit, namely this amount. And again, this can be de-randomized by dynamic program, again, similarly to the knapsack problem now. It's now a bit easier because we have a gap here. We can spend part of the gap to make the rounding simpler. And yeah, that gives the overall result. So we resolve the LP relaxation up to this factor. Randomized rounding would lose this factor. A deterministic rounding loses this slightly larger factor, and then we get an overall d over 2 approximation. So now I'm almost at the end. A few words on the lower bound. So we reduce the vertex deletion problem and directed acyclic graph to our problem. So given an acyclic graph and a parameter k, we ask for a minimum number of vertices to delete so that there's no path of length k any longer. So in this example, dvd2, we could remove, delete these two vertices, and then the remaining graph would not have a path of length 2 any longer. And again, Svensson showed that this problem cannot be approximated by any factor less than k, assuming unique gains conjecture. Achieving k is actually quite simple. And we do this in 2 steps. First, we reduce the dvdk to the time cost theta problem, or that's actually later it will be the second step. Yeah, that can be done. We use such an, or we take such an instance, and each vertex is on a level. It's acyclic. We can define a leveling, and then we have a column for every vertex, and we will have a round bubble for every vertex in the level where it was assigned to. And now you find this structure also in here. And in addition, we have these representatives in the other levels, which actually don't have a choosable delay, but just a fixed delay of d. And we connect them downwards. And from the, always we have an arc that is in the original graph, and if the level is increasing from one vertex to the other. And one can show that, this is a reduction that preserves the depth. So if this depth would be d, this depth is also d. It's obvious. And the important thing is that if we choose delays, fixed delays of d here, and choosable delays of d plus 1 on these bubbles, then the path or the path with j vertices in the original graph correspond to chains with delay d squared plus j if nothing is accelerated on the right hand side. And so to delete such path, we need to delete these chains, and that is the one part of the reduction, but these instances need not be depth bounded, and that's then a bit more complicated. So we take for an input graph the tensor product of that graph with the acyclic tournament on d vertices. So an example here, the input graph would be just a path, and then the resulting tensor product would be this graph. Now one can show that the optimum solution to kill all path of length k is upper bounded by d times the optimum in the original graph. That's fairly simple because you just take a solution from here and implement it in all of the d levels. And then the lower bound shows that if we have d plus 1 minus k times the optimum solution in the original graph, that is the lower bound for this. And then setting d roughly to k implies the Sartre results. We first apply this reduction to reduce dvdk to depth bounded dvdk, and then reduce the depth bounded decay to the time constraint problem. And yeah, that's my last slide. So we have seen a D-half approximation, a non-D/4 approximability, plus this factor 2, or this plus 2 is still there. And of course, open questions is, can we close this remaining gap? And one way to that would be to study maybe how I mean, we know that time constraint is a special case of bipartite hypergraph vertex cover, but maybe we can also reduce it the other way around without losing too much in the depth. So if we would get something that is better than a depth of 2D, if the hypergraph had depth D, then we would already get here a better approximation, inner approximability result. And yeah, that concludes my talk. Thank you.